Hi guys, welcome back to our free Euclidean geometry course. And last time we looked at basics on part 1, and then on part 2 we looked at theorem 1, which talks about the line from center perpendicular to a chord bisecting the chord, or the line drawn from center to the midpoint of a chord which is perpendicular to a chord. Right, so this is part 3, and we'll be moving very fast from now onwards. So the first theorem is a bit disconnected from this one, but everything we'll do from this one onwards will be interdependent, okay? Which means you are going to be using this theorem to prove other theorems, and using other theorems to prove many more other theorems. Hence I'm saying like they are interdependent on each other. Without wasting any time, today we should be looking into subtended angles. Now, what do we mean by the word subtended angles? Well, I don't know any formal definition of this, but the way I understand it is you can think of subtended angles as if it's created angles, maybe an angle that is created. What I mean by that is, let us take a simple circle like this one, and then remember when we looked into the basics or the components of a circle, we spoke about something called an arc, right? So let's say we have these 2 points that form an arc, point A on the circumference and point B. Right, then we have a line that is drawn from A, goes maybe to the circumference like that, and also another line that goes from A to B, from A and B, and it goes there. And then let's have more lines, maybe from A to B, going that side. Let's call this one angle C, angle D. Let's call this one O, this whole angle O. So A and B subtends or creates. How you do this is you try to trace back. So your initial point is A and B. You trace where the line A goes, where it meets line B. Wherever they meet, that's what we call a subtended angle. So they create or they subtend. So A and B subtend what? They subtend angle C, where? At the circumference, because it's lying on the outer part of the circle, like that. And also what? Also A and B are going to subtend another angle. Which one? When you do the tracing again, you will see that the arc AB meets exactly where? At D, which is at the circumference. I suck at this, so it goes like that. Right, they meet right there. So A and B subtend angle D where? At the circumference again. But that's not the angle. That's not the only angle which A and B subtends. A and B also subtends what? A and B subtends the angle O, but where? At the center, because O is the center of the circle in this case. They subtend angle O at the center. It's like they create angle O at the center. Always remember that. Okay, so we'll be looking more into subtended angles today. And if you look at this, let's think about it. Which angle is subtended by CD? C and D subtend which angle? Tracing again, there's point C, there's point D. When you go from C, you will meet at B. When you go from D, it goes exactly there. So they subtend the angle B, where? At the circumference, subtend angle D, right? And we only look at, sorry, not angle D, angle B. They subtend angle B. We don't only look at the circumference, right? It's the circumference and the center. There's another angle there which is subtended by C and D, but we won't be paying attention to this. In most cases, we will only be dealing with the center or the circumference. Those are the only angles of interest we are looking for. When either an arc or a chord subtends an angle at the circumference, or it subtends an angle at the center. Makes sense? Okay, so the first theorem into that we are going to look into states that the angle subtended by an arc, remember an arc is just these 2 points right here, right? The angle subtended by an arc at the center of the circle, this is the angle at the center. So you see, you're tracing A and B, they meet at the center, which is O, subtending this angle. Is double the angle, is double the size of the angle subtended by the same arc at the circle on the circumference now, which means the same arc is going to subtend another angle where? At the circumference. So this angle which is at the center is going to be twice that one at the circumference. So the reason you are going to use is this one, and you don't have to write it in full. So it's angle at center equals to 2 times angle at what? 2 times angle at circum, and just stop there, right? Always remember this. But like we said, every theorem comes with a proof. So these are all the different ways, these are all the different situations for angle at center. We will only prove this one. I will just show how this one and that one works. Okay, you can look into their proofs, but you barely get them in an exam situation. So okay, so let's look into this now. We have the following. Remember, what we have is a circle with the center O. Remember what I said the last time. Whenever you are trying to prove a theorem, what do? You first start by stating, right? You are required to prove. Let's check. Let's start some construction. Remember, this is A and that's B. So we are required to prove that the arc AB, which subtends that angle at the center, which is angle AOB, like that, right, will be twice that angle, which is angle C, will be twice angle C, like that. You are required to prove that the angle AOB, which one is it? This angle right here is equals to what? Twice angle what? Twice angle C. C, which is that angle at the circumference. Okay, so how do we do this? So after stating what you are supposed to prove, you check what you are given. If there's nothing of importance on the given statement, you can just skip it. So here I'm not given anything of value, so the given statement you can just ignore. Then you go straight to the construction. You cannot prove a theorem without constructing. So for the construction, we are going to construct a line that runs from point C through the center like that. So we are going to construct, let's call it CD, construct CD like that. Then we start naming. So we are going to call this one O1 and O2. We are going to call this one C1 and C2. Okay, then we go for the proof itself. So this proof now depends. We are going to be using the exterior angle of a triangle to prove this. So the proof goes the following way. We are going to separate the two triangles, this one and that one. How so? We have the line which runs like this, right? We have a line that goes something like that. Then we have a line that runs from C all the way to A, something like this. Then we have a line that runs from the center, which is O, to A. So that's the left side. This is C, that's A, that's O, and then we have D. This is D1, sorry, that's O1, and that's C1, right, as you can see now. Okay, so how does the proof go? A lot of people like to use the let x. Let's go for that method. Let C1 equals to x. Let the angle C1 equals to x. There you have it. This part right here is now called x. It's angle x. And then remember now, the line OC is equals to the line OA. Why is that? This is a radii. Remember, a radius is a line that is drawn from the center of the circle to the circumference. So this is equals to that. And if these two lines are equal to each other, then it means that angle C1 will be equal to the angle A. These are the properties of an isosceles triangle. Remember, an isosceles triangle has two equal sides, and the angles opposite those equal sides are also equal. So angle C1 is equal to angle A, but remember we said C1 is equal to x, right? So these are what? These are angles opposite equal sides. And then from there, we are going to use what? The exterior angle of a triangle, which tells us that the exterior angle, which is this one, is equal to the sum of the interior opposite angles. So angle O1 has to be equal to what? Has to be angle C1 plus angle A, right? But C1 and A are equals to each other, so it will be none other than x plus x, which is 2x. Why? This is the exterior angle of a triangle. And then from here, we are done. We go to the other triangle. Remember, this thing has two pieces like that. There's the other part which runs like that. Then we have a line that is drawn from C all the way to B, and then we have a line that runs from what? It runs from O all the way to B. So let me draw this the way it is. So we have something like that. So this is, remember, this is C2. And then what do we have here? We have O2, then we have B right here. So the first thing we are going to let again, let's let C2 equals to something else. We are going to let angle C2 equals to Y. So once we have this as angle C2, which is equals to Y, let's not forget that this line right here will be equals to that, right? OC will be equals to OP. Why is that? Because this is a radii. Both radiuses, radii in plural form. But this forms an isosceles triangle, and once this is an isosceles triangle, it means this and that should be equals to each other. So angle C2 should be equals to angle B, and they should be both equals to what? They should be both equals to y, because C2, we let C2 equals to y. These are what? These are angles opposite equal sides. And once we have that, then we can move on. We can see that angle O2, exterior angle again, will be equals to angle C2 plus angle B. But C2 and angle B are equals to each other, and they are both equals to y. So that will be 2y based on what? On the exterior angle of a triangle. Then from here, then we can go back now. Remember what we just proved. We just proved that O1, let's look at AOB. This whole angle AOB right here, AOB is equals to what? Angle AOB is equals to O1, angle O1 plus angle O2, right? As you can see, there's no reason for that. But O1 was calculated to be equals to 2x on that one. So we have 2x. And then we calculated O2 on the second step to be 2y. So it's 2x plus 2y, which is none other than what? AOB will be 2. We factor out the 2. It's x plus y. But remember now, we let this one be equals to x, and then we let that one equals to y. So the whole of angle C is x plus y, because angle C is basically what? Angle C is equals to C1 plus C2, angle C2 plus angle C1 plus angle C2. So C1, which is x, and that is y. So wherever we see x plus y, we substitute angle C. So this is 2 angle C. As you can see, we have proven what we wanted to prove, that angle AOB is twice angle C. Right. And then this thing comes in 3 different ways now. I usually call it okay, I gave it my own name so that I don't forget it. So one of these I call an arrow, right? An arrow like that. The other one, which is called a butterfly, right? It looks like the wings of a butterfly. And lastly, the other one is called a diamond. So these are all the different situations that you can have with angle at the center. So the first one is this one, the one we just proved, whereby you have what? You have an arc subtending an angle at the center. Let's assume that this is our center O, and the very same arc subtending an angle at the circumference. You see, it looks like an arrow, right? Whereby this is twice that. Mark the center first. And then we have the second one, which looks like a butterfly. How so? Because now we have that angle. We have this, our central point, which is that. So this angle runs from this, goes to that, and then it goes to the circumference again. So it crosses like that. I don't know, maybe we can have the body of the butterfly going from here. Maybe. Yeah, but that's the reason why I call it a butterfly. So this is the angle at the center, which is twice this one. Okay. And then we have the last one, which is the diamond one. Okay, so you need to be careful when it comes to this one. It's a bit confusing for many people. So if we have this as our central point, we have an arc. Which arc? The arc, which is maybe this one. It subtends an angle at the circumference. This is the arc AB, right? Subtending that angle there at the circumference, this one. Okay, so the very same arc goes on to subtend the angle at the center. But which one? That one there, which is a reflex angle. It's greater than let me see. Yeah, it's a reflex angle, which is that. So that's the one which is twice that. Let's look at this. Let me label this. This is AOB, and that's C. Let's do it A again, B, and that's O, that's C, like that. Let's call this one C. So as you can see, when we trace, this arc subtends with angle AOB, and this angle that it subtends, this is the obtuse. So there's obtuse, and that's reflex. Always remember that reflex greater than 90 degrees. When you take, how I remember this is, when you take underneath or below, you also take below. When you take above, you also take above. Okay, because we can just combine the two theorems. We can combine, not the two theorems, we can combine the two situations for what? For the diamond and the arrow to get this, whereby this now, this is related to that. In fact, that one, the reflex is twice what? Is twice that one. And then when you take below, you take below. So it's below and below, it's above and above, like that. I hope it makes sense. Then let us go into the application of this. First of all, that's what we have. Right, now the trick is you always need to identify the center. And remember the theorem, it says that the angle subtended by an arc at the center of the circle is twice that subtended by the same arc at the circumference. So this is the center which I'm going to mark in red. This is twice everything. It's twice all those angles. So let's see. The arc AB goes to subtend that angle, which is angle AOB, and the very same arc goes on to subtend another angle where at the circumference. So in fact we are going to write this as AOB, which is twice C. Do not write it the other way around using a half or something. It's gonna get confusing. Remember the reason this is angle at center equals to what? Angle at center being twice the angle at what? At circumference, like that. Okay, so what do we have? We are going to have that this is AOB, which is twice what? Twice x, because angle C is x. AOB is 130 degrees, which is equals to what? Which is equals to 2x divided by 2 divided by 2. And what's that? Angle x should be 65 degrees. Okay, let's try the other one now. We have this situation right here, the butterfly thing. Now as you can see, we have our butterfly right here. That's our butterfly. Those are the wings. So what do? That's our center now. That's the angle which is subtended. We have our central point, which is AOB. So the angle AOB, which is the angle at the center, will be twice the angle. As we trace, you can see that the arc AB subtends that angle of 50 degrees at the center, but the very same arc subtends another angle which is y at the circumference. So AOB should be twice y again for the very same reason. Angle at center equals to what? Equals to 2 times angle at the circumference. But AOB is given to be 50 degrees, which is 2y divided by 2 divided by 2. So y, which is equals to 25 degrees, just like that. Then we have the last situation, which is what? Which is the diamond. So when you look at this, you will see that the arc AB subtends that reflex angle, top and top. Remember, top and top. And the very same arc subtends another angle at the circumference, which is Z. So now I'm being specific. AOB reflex. In fact, even for this one, I should have been specific that it's AOB obtuse, but that's just show off, if I may put it like that. AOB reflex is equals to what? 2 times the angle C. Right, AOB reflex is 270 degrees, which is equals to 2Z. I didn't put a reason for this, but you know, angle at center being twice the angle at the circumference. So 270 degrees divided by 2 divided by 2. So Z is equals to what? Should be equals to 135. 270 divided by 2, which is 135 degrees. Okay, so this is the practical situation of it. Of course, it gets really confusing sometimes. So you do this exercise, but it's pretty much the same thing over and over again, right? Okay, let's just do it real quick. As you can see, AOB is the angle at the center, should be twice what? Twice the angle at the circumference. But AOB is x, so x is twice angle C, which is 62, which gives us what? X, which is equals to 124 degrees, like that. And then for the second one, let's check. The arc subtends the angle y, which is at the center. The very same arc subtends angle C, which is at the circumference. So y should be equals to 2 times 23 degrees. Angle at center being twice angle at the circumference. So y is equals to 46 degrees. Same thing. The arc subtends that reflex angle there, but the very same arc subtends this angle at the circumference. So basically, z is equals to what? 2 times 126 degrees. Right, so you do that, angle at center being twice angle at circumference. Goes on and on. Then there's a special case. The angle subtended by a diameter at the circumference of the circle is always 90 degrees. Okay, so be careful of this one. It's a special case of angle at the center, right? And you don't have to know this proof. They barely examine this. Up to so far, we know 3 proofs, right? Which is theorem 1, the one that talks about line from center to line from center perpendicular to a chord bisecting the chord. The other one, which is line from center to midpoint of a chord being perpendicular to the chord. And now we just proved angle at center. So this one says that if you have a diameter will always subtend at 90 degrees, like that. And it makes sense because think about it. if this is a straight line AP right here, this is a 180 degrees, right? So, and the 180 degrees appears to be angle at the center, which means for this chord, when it subtends any other angle at the circumference, it has to be 90 degrees, right? And the reason for that, it's angles in a semicircle or angles on a diameter. You can say angles on a diameter or angles in a semicircle, right? Whatever works out for you. Okay, let's move on. As you can see right there, we are asked to find the angle X using this one. Now let's see how we apply this one. Before we can find X, we can see we have a triangle, so there's no way of going straight for X, but we can see that PR is a diameter. Since in this scenario we were given that the point O is the center of the circle, so angle Q should be equals to 90 degrees because it's subtended by a diameter. So these are angles in a semicircle or angles on a diameter, which whatever one works out for you. So what do we have? Since we have a 90 degrees here, by default X should be equals to 90 degrees minus 55 degrees. Why? These are angles in a triangle, sum of angles in a triangle. By default X will be equals to what? 35 degrees, just like that. So over and over again. Look at this one. Even for this, we can see that AC is a diameter. Since AC is a diameter, the whole of angle B should be equals to what? Angle B should be equals to 90 degrees. Why? Because these are angles in a semicircle or just angles on a diameter. Whatever works out for you between these two reasons, whichever you remember first. Right, since we have B, but you can see that angle B is made up of two angles, which is the 52 degrees plus the angle X. Therefore, but we do have angle B, which is 90 degrees. So 90 is equals to 52 plus X. Hence, X is equals to 90 degrees minus what? Minus 52 degrees, which should be 38 degrees in the end. Okay. Same thing even for this one. They gave us this side to be 104, which means we can calculate that. And in fact, remember how we name the angles. You guys have a tendency of renaming the diagram and calling this one C1, C2, no, O1, O2, sorry. You cannot do that because on the memorandum, there's no labeling like that. You're going to call this one C1, C2, another person will call it O1, O2, and O3, which becomes a problem. So just follow the way it is named, which means if you want to name this angle, it's going to be COP, angle COP, like that. We are trying to find X and Y. So how will we find X and Y in this case? First of all, we can see that the whole of angle B is a 90 degrees. Angle B should be equals to 90 degrees because it's subtended by diameter AC. So it's angles on a diameter or angles in a semicircle. And then what do we have? Since we have a 90 degrees here, we need to find one of these two, either X or Y. If we find one of those, then we can find the other. Now let's think about it. How can we go on about this? Let's first find this angle COP. We can see that the angle COP should be equals to 180 degrees minus 104 degrees. Why is that? These are angles on a straight line, right? And once we have that, this gives us that the angle COP will be equals to 76 degrees. So right here we have a 76 degrees. Remember one thing now, the line OC will be equals to the line OP. Why is that? This is a radii, right? So this one is equals to that, which means angle C is also equals to angle Y. Why is that? These are angles opposite equal sides, right? Angles opposite equal sides. And then from there, what do? We have that when we do sum of angles in a triangle, so in triangle COP, as you can see, COP, we have the following. We have angle C, right? We have angle C plus angle COP, which is that angle of 76 degrees, plus the angle CPO, which is the Y, should give us 180 degrees. Why? These are angles in a triangle. And then from here, angle C, we just proved that it's going to be Y, plus COP is also Y, plus the one which you just calculated, and we got 76 degrees is equals to what? Is equals to 180. So 2Y will be equals to 180 minus 76, which is 104 degrees, like that. And once we have that 104 degrees, divide by 2, right? So this should give us that Y is equals to 52 degrees. And once we have Y, remember that X plus Y will give us a 90 degrees. So X is equals to 90 minus Y. So it's 90 minus 52 degrees. Okay, so this is how you apply it in such situations. Let us look into this one. Now this one wants us to find all the angles in alphabetical order. We start, if given that O is the center of the circle, find A, B, and C. You can pause the video, try it on your own, but this is how it's done. So let's look at the first one. Find angle A. If you look at angle A, first you draw there's A, then you do back tracing. You draw, you find out which points created or subtended angle A. You will see when you backtrack that this is going to take you straight to J first, and it's going to take you to M. So J and M are the points that subtended angle A at the center of the circle. And then we need to start from those points and check which other angle is subtended by this. And then you will see that it goes on to subtend another angle at the circumference, which is N. So this is angle at center now. And remember, we spoke about this. This looks like the arrow thing, whereby we take below, and then angle A is equals to 2 times 32. Why is that? This is angle at center equals to 2 times angle at circumference, like that. Okay, and then what else? Which means A is equals to 64 degrees, like that. And then from here we need to find angle B. But if you look at A and B, this is a revolution. That's angles around a point. When we add A and B, there's 2 angles right there, summing up to what? To 360 degrees. So this is A, and that's B on the other side, like that. Together they form a 60 degrees. So B is equals to 360 degrees minus angle A, which is 64 degrees. Makes sense? And what is the reason for that? This is a revolution. You can just say revolution or angles around a point. So we have this, which is what? 296. Angle B, which is equals to what? Which is equals to 296 degrees. We done? No. We should find angle C. Right, remember now how to find C. Let's check. If we trace back from C, we will see that C was subtended by the points M and what? And J. When we trace again, we will see that C is on the circumference. Another angle is what? Is that one, is the reflex B, which is related to what? To C. It's that diamond thing. So in fact, angle C, not angle C, angle B is twice angle C. 2 times angle C. Because angle B is the angle at the center. Why is that? Angle at center equals to 2 times angle at circumference. But B we do have to be 296. And then we have 2 C. Divide by 2, divide by 2. Just like that. Makes sense. 296 divided by 2, which gives us 148. So angle C is equals to 148 degrees. Okay, let's move on to the next one. Even for this, we should do it in alphabetical order. Right, here's one thing that you should know. Never write a step in your head. What I mean is, do not skip a step. Right, if you feel it's necessary, just write it down. Whatever helps you get the answer, then you need to write it. Let's look at that. Here we are given O, which is the center. Then we are given that OT is perpendicular, so O is the center first. Right, and we are also given that OT is perpendicular to what? To MN. Okay, so by default you can find angle A. Angle A is equals to 90 degrees. Why is that? The reason is OT is perpendicular to MN. Or you could have said, you could have used angles on a straight line, because we have a 90 here, which means it must be a 90 even on the other side. Let's find angle B. Where's B? There's B right here. How do we find B? Simple. So we are first going to say the line OM must be equals to the line ON. This is what I meant by don't write steps in your head. You need to have this somewhere. Why is that? This is a radii, because the line, this line is equals to that. They were both drawn from the center to the circumference, which means angle B will be also 32 degrees. This angle will be equals to that angle. And why is that? These are angles opposite equal sides. Right. And then what else? We should have angle C. How do we find angle C? By default, we calculated this to be a 90, which means angle C there will be equals to 90 degrees minus 32 degrees. Why is that? These are sum of angles in a triangle. So it's angles in a triangle giving us what? Angle C, which is equals to 58 degrees. And this will be the same thing for angle D. Angle D will also be 58 degrees on the same reason as that. Right. So what else do we need? D. From C, from D we need to find E. How exactly will we find E? Remember, we're still doing it in alphabetical order. Okay, so how will we find E? Let's try it the following way now. The first things first, we can see that let's just isolate that triangle. It runs from here, it goes to this, then it goes to that, right? And we can see one thing for sure, that the line OR has to be equal to the line ON, and this is a radii. They are equal to each other. This is equal to that, and for that case we have angle E, which should be equal to angle G, right? And these are angles opposite equal sides. And then once we have that, we can use the exterior angle now. Remember that the exterior angle, which is D, is equal to the sum of the two interior opposite angles, which means E plus G should give us what? Should give us angle D. Why? This is the exterior angle of a triangle. Okay, and then from here, E plus G are equal to each other, so we can just have it as 2E, which is equal to D. Then we divide both sides by 2, but we do have angle D. Angle D was calculated to be 58, so it's 58 divided by 2, right? So we have that as what? As 29. So angle E is equal to angle G, and they are both equal to 29 degrees. And you are going to do the same thing even for the other one, for F and H. Same approach. You just isolate that triangle, use the exterior angle, then you're done. Of course, to find J and I, you can either use angles in a triangle, or you can just use angles on a straight line. Up to you. So that's how you apply this. Right, we will also look at angles that are in the same segment, or the angles that are subtended by the same chord. So now let's look at this. Remember, we spoke about subtended angles. Look at the chord AB. If you look at AB, you will see that first of all, which angle does it subtend? It subtends the angle there, which is angle G, where at the circumference, but subtends another angle at the circumference again. So the angles that are subtended by the same chord at the circumference are equal to each other, and we call these ones angles in the same segment. Right, always remember this, on angles in the same segment. The angles that are subtended by an arc or a chord at the circumference, same arc, they are equal to each other. But of course, remember, we respect the center. Once you start to have the center, now it becomes a different story. Look at the chord AB again. Chord AB goes on to subtend that angle AOB at the center now, but goes on to subtend another angle, which is angle F at the circumference. So the angle AOB must be equal to twice the angle F, because one of them is at the center, one is at the circumference. So it's the same scenario even for this. Chord AB subtends angle O at the center, but it also subtends angle G at the circumference. So this one is twice that, always. Okay, so let's look into this now. How can we work this out? O is the center of the circle, and A, B, C, D, and E are on the circle. BAD is 21 degrees. Where's BAD? BAD is this one right here. What else? AB is 60 degrees. There's 60 degrees. Okay, fine. Calculate V, W, X, Y, and Z. So we are going to follow that order now. How do we find V first? You go to V, you mark that angle. Then you do a trace back using your index finger that, oh, this angle was subtended by that. It started from point B, and then we have another point, which is point D. Then we are going to trace back to find any other angles that are subtended by B and D. And when we trace, we will see that there's another angle, which is A, right there. A was subtended by what? By B and D. And where are they? A is at the circumference and E is at the circumference. So angle V is equal to angle A, and they are both equal to 21 degrees. What do we call these? These are angles on the same segment. Angles in the same seg. Like that. Okay, so at least now we have angle V, which is where this is 21 degrees. Then we should find W. Where is W? We go to W, we mark W, and then we trace back. W was subtended by that arc, which is what? Which is BD. But the very same arc goes on to subtend another angle at the circumference, which is angle A. Remember, angle at center being twice angle at the circumference. So W is twice of 21 degrees. Why is that? This is angle at center equals to what? Equals to 2 times angle at circumference. Okay, like that. And then we have W to be 42 degrees. And once we have that, we need to look for more angles. Let's see. Now we have this one. This is 21 degrees. That's 42 degrees. We should find what? X. but look at this, x and w, they form that, right? So x plus w should give us a 360 degrees. Why? Angles around a point, or simple revolution, we have w, so x will be equals to 360 degrees minus w. W is 42 degrees. Okay, so 360 minus 42, which gives us 318. So x is equals to 318 degrees. From there we should find y. We go to y. Y was subtended by that arc BD, right? So it's this above, and BD also subtends that. It's that diamond thing we spoke about at the beginning of the video. So x is twice of y because x is at the center. Y is this. This again is angle at center being twice angle at the circumference, blah blah blah. So x we do have to be 318 degrees. Is twice of y, which means y is 318 divided by 2. So 318 divided by 2, which gives us 159 degrees. Right, now to find z, how will we find z? Same thing over and over again. We go to z, we mark the angle, we start to trace back which arc. It started from point E, we trace back again, we find point A, but the very same arc E subtends another angle there, which is at the circumference as well, the 60 degrees, angles in the same segment. So Z will also be 60 degrees. Why? These are angles in the same segment. They are subtended by the same arc, sometimes subtended by the same chord. Okay, angles in the same seg, like that. Okay, then we move on. Let's see, you do this one. This one will be yours, but even for this you have to find the angles in alphabetical order, so pretty much the same thing over and over again. I will just highlight and then you will do it on your own. Find A first. How do you find A? You go to A, you mark A, then you trace back. You will see that A was subtended by that arc, which is what? Which is QP. You trace back again, which other angle? It subtends that angle of 27 degrees. So those two are equals to each other. A and 27 should be equals to each other. How do you find B? You already have a right angle triangle there. So B is 90 minus 27, sum of angles in a triangle. How do you find C? Let's look at C. There's C. Okay. C is subtended by the arc NP, but NP doesn't subtend. Oh, NP also subtends D at the center of the circle. So it's a bit difficult to find C at this point because we cannot use that. Okay, fine. How exactly can we find C? Let me see. That's 90 degrees. Then we have G. We can calculate G, but we need to find C before G. Okay, but this is easy though. O is the center of the circle. Since O is the center of the circle, then this becomes a diameter. Since this is a diameter, the whole of angle Q should be 90 degrees. Why? Angles in a semicircle. So B plus C should give us 90 degrees, and we already have B, which is 90 minus 27, and that's exactly 60. It's at 53 degrees. Yeah. So you do that. C, D, you need to find D now. If you look at D, you will see that D and C are related. In fact, D is twice of C, angle at center being twice angle at the circumference. Find E, E is 90 degrees. Find F, F is 90 minus angle D. Find G, sum of angles in a triangle can give you that. And then what else? You go for this one. Let's do number 5 together. On number 5, what do you have? Number 5, first things first, you have you are supposed to do this in alphabetical order. T, U, V, W, X, Y, Z. Let's go for T. We go, we mark T, we trace back. It's point B. We trace, it's point C. So we have the arc that subtends angle T. It's BC. Which other angle is subtended by that? We will see that BC also subtends another angle at the circumference, which is angle D. So we have angle T now. T is equals to angle D, which is 40 degrees. Why? These are angles in the same segment. Okay. And what do we have? We have angle. We should find U. How do we find U? U was also subtended by the very same BC at the circumference again. Right. So that one is also what? That one is also 40 degrees. U is equals to 40 degrees. Let me see. Yes, U is 40 degrees. And these are still angles in the same seg. Okay. And then let's find let's find V. If you look at V, you will see that V was also subtended by BC, but at the center now. So angle V should be equals to twice of U, which is 80 degrees. And this should be angle at center being twice angle at circumference, like that. And then VW, where's W? There's W. Which one subtended W? Trace back. We trace back to point A, sorry. We trace back to point B. But then when you trace, you will see that the very same subtends another angle, which is 21 at the circumference. So W is 21 degrees. W should be 21 degrees. Again, this is angles in the same segment, right? Let's see, what else do we have? W, we should find X. Let's look at X. Which chord subtended angle X? You will see that X was subtended by B and A, but X is at the center. The very same arc subtends what? The 21 degrees. So X should be twice of 21, which is 42 degrees. This should be angle at center being twice angle at the circumference. Okay, and then what else now? We need to find Y and Z. But first of all, you can see, since this is O, OA has to be equal to what? To be equal to OC. Alright, this is a radii. And this means that the angle Y will be equal to the angle Z. And these are angles opposite equal sides. Alright, and from here, what do we have? We have that this whole angle here, which is AOC. AOC added to Y plus Z should give us 180 degrees. And this should be what? Angles in a triangle. But we have AOC. AOC is none other than X plus V. Remember, we found X plus V. There's V, there's X. Plus, we found Y and Z to be equal. So we can just write it as 2Y. Like that. So X and V, which is 80 plus 42. Right. Plus 2Y should give us 180 degrees. So you solve this. Find out what that is, then you're sorted. Okay, and this marks the end of the lesson on subtended angles theorem. I don't know the theorem numbers, you just have to know how to state and how to apply them. Okay, see you on part number 4.